Hello, learners, and welcome to our live video event for. We're going to do a little bit of Lenz's law, and then I'm going to do a really quick kind of Q&A for your take-home test. So let's take a look at the board. So Lenz's law describes how a changing magnetic field can induce a current in a wire. So first we need to talk about flux, specifically magnetic flux. Now what this is basically an amount of magnetic field entering a given area. And for instance, if I've got a current carrying loop like this, or it's just a wire loop, and I've got magnetic field that's directed into the page, okay? Well, if I move my current carrying loop to the right, what I'm doing is I'm changing the amount of magnetic field that's entering this given area. And it's that changing magnetic field that creates a current in our wire here. So the flux, the magnetic flux, is equal to the integral of B times dA. And for those of you that are in APB, we will always have a constantly changing area or a constantly changing magnetic field. So I'll talk to you about magnetic flux here in just a minute. But this is basically an equation to describe how either the magnetic field might change or how the area might change. So flux is basically how much magnetic field enters a given area. And current carrying loops have a really strange property where it's kind of like an electromagnetic inertia in a sense. They resist changes to the amount of flux that they have. So for instance, if I go back to my current carrying loop, and I've got a magnetic field that's directed into the board like this. Okay. If I pull this thing to the right with a certain velocity, v, well, what it's got is no magnetic field through it initially. But then it's going to have magnetic field through it. So there is an increase in flux. Well, this loop doesn't like a change in that flux. So what it does is it gives itself a current to give itself a magnetic field that opposes this change. So I increase the amount of field that's directed in. Therefore, the wire kind of counters this change, and it tries to give itself a field that's directed out. And the way it gives itself magnetic field is by inducing a current in that loop. Okay, so if this thing, as I pull it in, the field starts increasing in, it tries to give itself a field out. So how it's going to do that? Well, imagine I grab, say, this wire right here, and I grab it so that the current is going this way, and my field comes out. Well, if I grabbed this wire, same way, my field would come out. So what this wire is going to do is as it's entering this area where you've got field going in, it tries to give itself field that goes out. And the way that it's going to do that is by giving itself a current that moves around counterclockwise. Now, Here's a neat trick that you can do. You know that this thing wants to give itself field out. So point your thumb in the direction that it wants field to counter this change. It wants field out, and you wrap your hands, and your hands will wrap in the direction of the induced current. So this change in flux, change in magnetic flux, induces a current. And that current, again, this is geared towards AP Physics B, is the change in magnetic flux with respect to time. Now, how our flux changes, well, it can depend on how fast that loop was pulled in. The faster I pull it in, the greater the amount of change in flux there will be, which means the greater, again, this is induced EMF, or electromagnetic force, which is basically the voltage associated with this wire. So let's try a different example here. Let's say that I've got a wire, and then it kind of goes this way, and then this way, and I've got this guide rail, this conducting piece of metal that can slide side to side, okay? And let's say it slides this way with a certain velocity v. But all through this thing, there is magnetic field that's directed out. Okay, again, out of the page. Out of the page. Okay, so as this thing slides to the right, there is going to be a current induced in this loop right here. And I want to know the direction of that current. So if you think about this, as I pull this thing to the right, I'm increasing the amount of basically dots, which represent magnetic field, and increasing the amount of dots basically increases the amount of flux. So I'm increasing the amount of flux out. Well, the loop doesn't like that. It wants to maintain whatever magnetic flux it had before. And so if I'm increasing the amount of flux out, it's going to try and give itself a flux in. So if I point my thumb in, I'm going to curl around, and I'm going to get an induced current that's going to run like this, clockwise. Okay, now how much current? Well, remember that the voltage is equal to the change in flux over the change in time. Okay, so change in flux over change in time. How is the flux changing? Well, remember, flux is equal to the integral of B times dA, how the magnetic field and area change with respect to time. Okay, or how the magnetic field and area, the product between those two. Okay, well, again, this is for APC. If I take the derivative of an integral, I just, in a sense, just cancel out that integral. So my voltage would then just become B times dA over dt, how my area changes with respect to time. Now, the amount of magnetic field is a constant. It doesn't change. How area changes with respect to time? Well, if I think about the area of my loop, let's say that this thing has a length L. Well, L doesn't change. What changes is the width. And that width changes as this bar passes to the right. So my width is really dependent upon the velocity, how far I've gone. Well, if width is dependent upon my velocity, then think about how area would change with respect to time. It would be your area would be length times your width with respect to time. But width is just going to be equal to how far I've gone. So BL times V, that's going to be the induced EMF here. In APB, that holds for us too. So that is the voltage associated with this wire. If you knew the resistance in this wire, you could figure out the current because you know that voltage equals IR. You could figure out exactly how much current is flowing through that. So big ideas here. Loops try to counter however you're changing the flux. So if you're increasing the flux, it doesn't want that to happen, so it will try and counter that increase in flux. Let me do one more example, and then I'll drop some hints for your take-home test. Let's go back to our ring of wire here. Let's go back to our magnetic field that's directed into the page. And we already said that as I pull this thing to the right, it gets an ever-increasing amount of flux in. It doesn't want that to happen, so it tries to give itself a flux out. So initially, I get a current that's flowing like that. But that only happens as I pull this thing in. Once it's completely inside the magnetic field, well, then there is no longer any change in magnetic flux, which means there would be no longer any current. So I would only get a counterclockwise current as this thing was entering the field. Now, what about when it's exiting the field? As it's still moving this way, well now, as I pull it out, the amount of flux going in is decreasing. And it doesn't like that. This loop is never happy. It either wants no flux or then, okay, I got flux and now I want the flux. So as I pull it out, the amount of flux in is decreasing, and it tries to counter that decreasing flux in by giving itself a current that would be going in the opposite direction because it wants to increase the amount of flux going in, and it would give itself a current going clockwise. Okay, so that's the basics associated with Lenz's law. It just describes the direction of current as the flux changes. Okay, I want to talk to you about your first problem in the take-home test. And your goal is to figure out minimum height so that your block will just reach the tippy top, but remember that there is friction present on this block as it's sliding up. Whoops, Fk, and then Fn. So, and if there is friction present, that means that there is work done. And work, as long as it's a constant force, is just F delta R cosine. I'm reluctant to say theta because I called that theta, so I'm going to call it cosine of phi. And just remember that that is the angle between delta R and the force that's doing the work. Now, if you're thinking conservation of energy, you're on the right track with this. The tricky part is getting H when you also don't know how far the block slid, because how far the block slid depends upon height. But remember, you make a triangle here, and you know this angle. You can get R in terms of H, or you can get H in terms of R. Solve for one first, and then solve for the other. The next problem is a thermodynamic problem. And the big thing that I want to kind of remind you on here is that internal energy, or delta U, is directly related to the change in temperature. So as temperature changes, internal energy changes. So Again, temperature changes as you move to different positions on the map. And the last question asks you for the change in internal energy for the entire cycle. For the entire cycle, meaning you start here, and then you get back to where you started. Also remember the ideal gas law, PV equals nRT. You don't have to worry about converting pressure to any special units. Just whatever unit you can find for pressure, give me that unit. The last question is our capacitor question. So we have a battery, capacitor, some more capacitors, and this isn't your exact circuit, but it will work for our intents and purposes. Okay. And you wanted to know the charge on, I can't remember, I think it's like C4 or something. You go about it the exact same way you would a resistor circuit. Start by getting the equivalent resistance and then work your way back to this capacitor. Simplifying it down one step at a time. Go these two first. How do series capacitors simplify into an equivalent resistor? Simplify that one down, and then if you have to, redraw the circuit with this thing now simplified into one capacitor. Then, as you work back, whatever you solve for this, take whatever made up that capacitor with you. So if this thing is made up of two capacitors in series, take the charge with you, because series capacitors share the same charge. If this equivalent capacitor was made up of two in parallel, take the voltage with you. And I've got a video tutorial on voltage on capacitors in case you have forgotten. So, other than that, that's all I got for you guys for tonight. So thanks for tuning in, and have a lovely evening.